Vectors are quantities defined by both magnitude and direction. So we can write vector. A vector is defined by both magnitude and direction, whereas a scalar is defined by magnitude only. Right, so there you have it. You get your 2 marks just by doing that. Right, the electric field strength E at a distance E from an isolated object, blah 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 blah. Use the definition of field strength to show that E has SI base units of that. Well, electric field strength can be defined as the force per unit charge in an electric field, the force per unit charge at that point in an electric field. Right, so since it's force per unit charge, it means that E has got units of newtons per coulomb. And newtons, force, is mass times acceleration. So we can write that in SI base units as kgs meters per second squared. That is force. Then coulombs, charge, its current times time, which is ampere seconds, like that. Right, so rewriting this will give us kgs meters per amp and s to the minus 3, just as they want there. That's what we get. Right, we are on to item 2 now. We are going to use the units of E to determine the SI base units of B. So we are going to make use of this equation here and these units that we have obtained. How are we going to do that? Well, this is how we are going to do it. This is how we are going to do it. We have been told that E is equal to Q divided by X squared B. So the units of E are kgs meters per amp and s to the minus 3. Those units should be the same as the units on the right hand side. We assume that this equation is dimensionally consistent. So the units on the right hand side are AS for Q, because Q is charge, over x squared. X is distance, meters, so x squared is meters squared. And then the units of B will go right there. Right, so to get the units of B, all we need to do is some algebraic manipulation. Right, so the units of B are going to be given by this expression. But that's a minus 3 right there. That's a minus 3 right there. That's a minus 3. Right, then we multiply by but those are the units of B, and they simplify to give us A squared m to the minus 3 s to the power 3 or rather s to the power 2, s to the power 2 right there, because these two will this will divide into that one, so we'll get s to the power 2 and per kg. Those are the units for B. That's what we get right there. The question says define acceleration. Well, acceleration is the rate of change of velocity with time. Rate of change of velocity with time. Right, the rate of change of velocity with time, that's acceleration. The next part, a steel ball of diameter that is released from rest and falls vertically in air as illustrated in Fig 2.1. Right. A horizontal beam of light of negligible width is a vertical distance of 0.28 meters below the bottom of the ball. When it is released, the ball falls through and breaks the beam of light. Explain why the force due to air resistance acting on the ball may be neglected when calculating the time taken for the ball to reach the beam of light. Well, the ball has a very small diameter, so the air resistance acting on the ball is quite negligible, because air resistance depends on the dimensions of the object falling through the air. So since this diameter is very small, the resistive forces due to air are very, very small compared to the weight of the object. So we can summarize all this by saying weight of the object is very, very large as compared to air resistance. Right, that's what we can do there. The weight is very, very large as compared to the air resistance of the ball. Air resistance. Right, we are on to item 2. Calculate the time taken for the ball to fall from rest to position P, where the bottom of the ball touches the beam of light. Right, so we have that diagram once again. Let's take a look at it once again. So we want to calculate the time taken for the ball to fall from there, right, to fall from there to there. Right, we are going to be making use of equations of motion there. What are we given? We are given the displacement. This is the displacement S. What else do we know? We know that G is equal to 9.81 meters per second squared. What else do we know? We know that at this point here, before the ball is released, U is equal to 0. Right, so we have got those quantities. U equals 0, G is 9.81, and S is 0.28. And we want to calculate time. Right, how do we calculate the time? We just find the appropriate equation of motion to use. Right, so the appropriate equation of motion to use in this case would be, S is equal to UT plus half AT squared. Right, now U is 0, so UT there will give us 0. So we'll be left with S is equal to half AT squared. And we know what S is. we want to find t. So t equals the square root of 2s over a. In this case, a is g, right there. Right, so that will give us the square root of 2 times 0.28, right, all over 9.81. Right, and that will simplify to give us 0.23892. Right, we have to leave our answer to a reasonable number of significant figures. So in the data that we've been given 0.280. So this figure is to 3 significant figures. So we should leave our answer to 3 significant figures, because that was 3SF. Let's leave our answer to 3SF. So we will have our answer as 0.239 seconds. That's our answer right there. Right, we are on to item 3. Determine the time interval during which the beam of light is broken by the ball. Right, okay, so here what we're going to do is we are going to find the time taken by the ball. Find the time taken by the ball to move through a distance of 0.28 plus the diameter of the ball right there, which is 0.08 meters. Right, that's the time interval. That's what happens when the beam of light is broken. The ball first falls through 0.28 meters, then it falls through an additional 0.08 meters, which is the diameter of the ball. So what is the time from when the ball is released? What is the time that the ball will take to travel through a distance of 0.36 meters? Let's find that time. Right, so time taken to travel through 0.36 meters. Again, we make use of the equation of motion, which says S equals ut plus half a t squared. In this case, our a is g and our u is 0, so S is equal to half gt squared. Right, we want t, so t equals the square root of 2s over g. That in this case our s is 0.36 meters, so we make sure that we substitute s with 0.36 meters right there. Right, if we input this into our calculator, we get 0.271 seconds. Right, so we keep this result 0.271 seconds, and we have to calculate the time interval from that the beam of light is broken. So remember time interval from release up to when beam is cleared, when beam is cleared, that is equal to 0.271 seconds. Right, and we have time interval from release to reaching the beam. Time interval from release up to when the ball reaches the beam, it's 0.032 seconds. So 0.032 seconds is our time interval right there. 0.032 seconds is the required time interval there. A different ball is released from the same position as the steel ball in B. This ball has the same diameter but a much lower density. For this ball, the force due to air resistance cannot be neglected as the ball falls. State and explain the change, if any, to the time interval during which the beam of light is broken by the ball. Right, so we have two factors at play. Firstly, the density is lower, which means the weight of this ball is lower. Secondly, the air resistance is greater. So the time interval for which the beam of light is broken increases because air resistance decreases the acceleration of the ball. Action by A on B causes an equal and opposite reaction, by B on A. That's what we can write there. Right, then we are on to part B. We are going to use the conservation of momentum to show that, or rather, we're going to use the conservation of momentum to show that the ratio of mass Y over mass X is 4. How do we do that? Well, the principle of conservation of momentum says that for an isolated system of interacting bodies, the total momentum in any given direction is constant. This means that momentum before collision is equal to momentum after collision, provided that the system is isolated. There are no external forces acting on the system. Right, so what is the momentum before collision? Before collision, we have mass x times 5v. After collision, however, we have the two masses stuck together and moving at a common velocity of v. Right, since we have v on both sides of the equation, the v's can cancel out and we'll be left with 5 mx equals mx plus my. Right, now if we take mx to the other side, it will be subtracted and we will have 4mx equals my. 4mx equals my, and this will give us the ratio my over mx. There you have it. And so we're going to calculate this ratio. The total kinetic energy of x and y before the collision is only the kinetic energy of x, because only x was moving. So kinetic energy is half mv squared. Right, so before the collision we had only x moving, so it's half mx times the speed of mx before the collision squared. This gives us 25 over 2 mx v squared. After collision, we have both x and y moving at a common velocity, so kinetic energy was half. Then the masses were combined. The masses were combined, and the velocity was just v, like that. This is after collision, and before collision we have this. The v squared can cancel out, then this and that will cancel out, and we will have 1 over 25 right there. Then we have to remember that my is 4 times mx, so up there, this thing here is equivalent to 5 mx. So we have 5 mx over mx. So the ratio will simplify to give us 5 mx all over 25 mx, and this simplifies to give us 0.2. That's the ratio there, 0.2. Then item 3 says state the value of the ratio in 2 for a perfectly elastic collision. Well, for a perfectly elastic collision, total kinetic energy before and after impact is the same, so the ratio is just 1. Right, then we have this. The variation with time t of momentum of block X is given right there. Right, what are we supposed to do? Block X makes contact with block Y at time t is 20 milliseconds. Describe qualitatively the magnitude and direction of the resultant force, if any, acting on block X in the time interval. Right. Now, the resultant force acting on block X is constant for the first, or rather is 0 for the first 20 milliseconds. Why? Because there is no change in momentum, which means there is no change in velocity, which means acceleration is 0, which means the resultant force is 0. So for the first 20 seconds we can write resultant force is 0. Resultant force equals 0. Or we can say no resultant force. Right, then for the other part, constant resultant force in the opposite direction. In the opposite direction. Constant resultant force in the opposite direction. Right, then for this part that says sketch the variation of the momentum of block Y with time t from 0 to 60 milliseconds. All we need to do is, firstly, Y was not moving, so its momentum was 0. Right, so in the first 20 seconds, the momentum of Y is 0. In the first 20 seconds, the momentum of Y is 0. That line there is supposed to be on the 0 mark. 0 right there. Then it changes, it increases as Y experiences a force from X. So it increases at a constant rate. Right. Then it becomes constant at that point. This part of the question, item 1, says state the principle of moments. Now the principle of moments says that for a body in rotational equilibrium, the clockwise moments are equal to the anti-clockwise moments at any point. Right, by using moments about pivot C, calculate force FB. Right, we have to go back to this diagram and we have to calculate some distances. Right, here we need to determine some distances. Right, what is the distance of this 380 Newton force? What is the distance of this force from the pivot C? This perpendicular distance of the force from the pivot C, it's 2.5 meters. Right, then we need to find the distance of the man from the pivot C. The man from the pivot C, this distance here. What is this distance? That distance there is 1.6 meters. Right, another distance that we need to calculate is the distance of the force FB from the pivot. What's that distance? That distance there that distance there must be 5 meters. That distance there must be 5 meters. We can now take moments about C. Taking moments about C, the clockwise moments would be contributed to by this force and this force. They contribute the clockwise moments. The clockwise moments would be 380 times 2.5, right, plus 750 times 1.6, right. These clockwise moments should be equal to FB times 5. Right, so this equation will give us our FB as 230 newtons. Right now, so we have this question here, this item 3. We are being asked to find the distance x that the man can stand as close to D as possible without tipping the beam. And one condition that we've been given in the question is that when FB becomes 0, the beam will tip, or is about to tip. So this force, we are going to equate it to 0. That will enable us to determine x. Right, so we are going to take moments about the point C. Take moments about the point C there. And if x is the distance that the man stands away from D, then this distance here happens to be 2 minus x. Right, so 2 minus x there. Right, so if we take moments about C, the clockwise moments are going to be constituted by this force, right, and the anti-clockwise moments will be constituted by the 380 Newton force. Right, so right, now let us use the principle of moments to find x. The beam is about to tip when FB becomes 0, but that's not where it tips, right? It's about to tip. So the system will still be in equilibrium. So we can say clockwise moments are equal to anti-clockwise moments. And the clockwise moments are 750 times a distance of 2 minus x. Right, 750 times 2 minus x. That should be equal to 380 times a distance of, well, this distance here, this distance there is supposed to be 2.5. Right, so it's 380 times 2.5. 380 times 2.5. Right, so that will give us x equals 0.733 meters. Right, since we have been given our answers in this case to two significant figures, this becomes 0.73 meters. Right, this is to two significant figures. Right, so that is our answer there. By the wavelength of a progressive wave, The wavelength of a progressive wave is the distance between any two adjacent wave fronts. Distance between two adjacent wave fronts. That's the wavelength. So we can write distance between two adjacent wave fronts. Distance between two adjacent wave fronts. That's what you do to get that single mark. The next part of the question says a cathode ray oscilloscope is used to analyze the sound wave. The screen of the CRO is shown. We are given the time-based setting and we are asked to find the frequency. How do we find the frequency? Right, we have to find the distance between two adjacent crests. The distance between two adjacent crests, that is from there to there, or any two adjacent crests. That distance there is 10 little boxes which are equal to 2 centimeters using the scale they've given us here. So this distance here is 2 centimeters. It's 2 centimeters. 2 centimeters. Right. According to the scale down here, we are told that 1 centimeter represents 2.5 milliseconds. So 2 centimeters is 5 milliseconds. That 5 milliseconds is our period. So period is 5 milliseconds. And from the period we can calculate the frequency. So frequency is 1 over period, which happens to be 1 over 5 milliseconds. This gives us a frequency of this question here. We should find the path difference between the waves meeting at C. So we need to find this distance. We need to find distance BC. We need to find what that distance is. And it's easy to calculate really because we have a right angle triangle. We'll employ Pythagoras theorem. We'll employ Pythagoras. So by Pythagoras, BC is supposed to be 20.8 squared minus 8 squared, which gives us 19.2. This is BC. Right. So the path of all the waves traveling from A to C will be the path of the waves from A to C will be this, and this gives us 8 plus 19.2, which is 27.2. Now the difference between 27.2 and 20.8 happens to be our answer. That's what they want us to do there. Right, that's our answer right there, 6.4. Right, that's how we show. Right, to explain item 2 there, we have to notice that these waves, when they meet at C, they have a path difference of 6.4 meters, which is 4 times the wavelength. Right. So since they meet at a whole number of wavelengths, they meet in phase. So to get your 1 mark, 1, we say here that the waves meet in phase. Waves meet in phase. Waves meet in phase. right? And 2, we say that there is constructive interference there, right? So that's what we do to get those 2 marks. Right, to answer item 3, we need to find the velocity of the wave. If we find the velocity of the wave, we know that there is a path difference of 6.4 meters. Then we'll just divide that distance with the velocity of the wave. But we know that the velocity of the wave is given by v equals f lambda, right? So the frequency, we found the frequency to be 200 Hz, and we multiply by the wavelength, which is 1.6. This will give us 320 meters per second. This will give us 320 meters per second. Right, so the 320, we'll then use it here. The time difference, delta t, equals, we now say, the distance, the path difference, 6.4 meters divided by 320 meters per second, and this will give us 0.02 seconds. 0.02. The next part of the question says the wavelength of the sound is gradually increased. Calculate the wavelength of the sound when an intensity maximum is next detected at C. Alright, so if the wavelength is being increased, the next time that we will have constructive interference at C is when we have this situation here, is when we have 3 lambda being equal to 6.4 meters. Right, so that is the next time when we have constructive interference at C, which gives us, this gives us lambda as being equal to, it gives us lambda as being equal to 2.13 meters. 2.13 meters. That is how we solve this question. Alright, let us suppose the question had said the wavelength of the sound is gradually decreased. The next time when we would have a maximum at C, the next time when we would have constructive interference at C, it would be when we have 5 lambda being equal to 6.4 meters. And this would give us lambda equals and so that's what we would have done there if the question had said the wavelength of the sound is gradually decreased. Kirchhoff's first law, which is otherwise known as Kirchhoff's current law, states that the sum of currents entering a junction is equal to the sum of currents leaving the junction. The other part of the question says the variation with potential difference of the current for a resistor X and for a semiconductor are shown. Determine the resistance of the diode for a potential difference of 0.6 volts. Right, so at 0.6 volts, at 0.6 volts, at 0.6 volts, the current is 7.5 milliamps. 7.5 milliamps. So the resistance R is voltage over current, which gives us 0.6 over a current of 7.5 milliamps, and this gives us, it gives us 80 ohms. Describe qualitatively the variation of the resistance of the diode as V increases from 0.6 to 0.75 volts. Qualitatively, so we're just going to say, does it increase, does it decrease? In this case, the graph shows that current increases, the resistance decreases. Right, now we have to find the voltage across the resistor and the voltage across the diode and add them together. The voltage across the diode happens to be 0.6 volts, because that's the voltage across the diode when we have a current of 7.5 milliamps through it from the graph above. Right, we're supposed to use Fig 6.1 to determine E. Fig 6.1 is this one over here. Alright, so we have the resistor and the diode connected in series, and there is a current of 0.5 milliamps through the resistor, which means 7.5 milliamps is this, which means that is the voltage across the resistor. And also that is the voltage across the diode. So we have 0.3 plus 0.6 to give us 0.9. That's E. That's how we determine E. The question says determine the resistance of resistor Y. We know that the current passing through Y can be obtained from the currents law. Currents entering a junction are equal to currents leaving. We have currents of 9.3 entering the junction, which means the difference between 9.3 and 7.5 milliamps the current that enters through Y. So this is the current passing through Y, and that current we have to divide it by E so that we get the resistance. So E was 0.9 volts, and we divide by 1.8 milliamps, and that gives us 500 ohms. That's our answer. So the power dissipated in the diode can be obtained from this formula. Power is equal to IV. Right, now we have a current of 7.5 milliamps, that multiplied by a voltage of the voltage through the diode is 0.6. Right, so we have this. That gives us a power that gives us 4.5 milliwatts. Right, so we have 4.5 milliwatts right there. 4.5 milliwatts. That's our answer there. Right, now to answer item 4, which says the cell is now replaced by a new cell of EMF 0.5 volts and negligible internal resistance. Use fig 6.1 to determine the new current in the diode. To answer this question, we need to look at our given graph. Let's look at our given graph. And the current is 0.5 volts. .5 milliamps. So this is the current through the diode. Now we are on to number 7. Determine the number of protons and the number of neutrons in the nucleus X. Right, so our alpha particle, this here, it can be written as, it's a helium nucleus, so it can be written like that. So in other words, we are saying from 238 we have removed 4. What is left over after removing 4 from 238? We are left with 234. Right, this is the nucleon number. What about the proton number? From 94 we have removed 2, so we are left with 92. That's the proton number. So number of protons is 92. Right, what about the number of neutrons? The number of neutrons is, it's 234 minus 92 to give us 142. That's the number of neutrons. Now on to B. For us to get the number of plutonium-238 nuclei that's required there, we need to remember that power is work done over time taken. So work is power times time. So 0.15 watts times 1 second to give us 0.15 joules. Right, so we need this much energy. Alright, so we have been told that this much energy is produced. This much energy is produced when one nucleus, this is for one nucleus, when one nucleus reacts. Right, how much is 5.6 mega electron volts? We can find here the number of joules in 5.6 mega electron volts. Each electron volt is 1.6 by 10 to the minus 19 joules. Right, so if we do the math, we get 8.96 by 10 to the power minus 18 joules. But this is one nucleus. So one nucleus is giving us this. One nucleus. So how many nuclei do we need to get 0.15 joules? Right, to get 0.15 joules, we need this many nuclei. 0.15 divided by 8.96 by 10 to the minus 13. This is the number of nuclei. Right, we get, from that we get nuclei needed.